Nice to meet you.
Yeah. So we had a lot of her help in organizing everything really, from permission at the administrative level to getting the student body together. So she's been very helpful all along.
Very cool.
And we have Swastik also, who you've been in communication with, and he is going to be the CAMS coordinator from the student side at IISER Tirupati. Yeah.
Cool.
Yeah. Terima kasih True Caller.
We are expecting more people to attend.
Yeah, so I guess we'll wait for 2 more minutes and start. Is that cool?
Somebody has a family.
Yeah, I think Swastik, you can start now.
Yeah. So hello and very good morning, everyone. I'd like to welcome you to today's guest session on behalf of Celestic. So I'm your host Swastik, and with me I have my co-host Amisha. So today we have 3 really special guests with us. So to introduce them, I would like to call Amisha. Over to you, Amisha.
Hello all, good morning and thank you, Swastik. So we have all wondered at shooting stars when we were younger and probably still do now. They're also quite often depicted in movies as well. If you've ever wondered what those rapidly moving blobs of light are, you're not listening. In the language of science, these objects are called meteors, and when they come in a group, we call them as meteor showers. Here with us today, we have 2 special guests who are going to shed some light on what meteor showers are, how they're formed, and much more. Before we begin, however, let's get acquainted with our guests over here. Firstly, we have Dr. Peter Jenskins. Dr. Jenskins is a senior research scientist in the planetary astronomy discipline at the SETI Institute. He currently runs the NASA-sponsored Cameras for All-Sky Meteor Surveillance CAMS project, which aims to confirm some of the meteor showers in the IAU working list. Since its start in 2009, CAMS has confirmed several meteor showers and has also discovered a new one. Dr. Jenskins is also the author of the book Meteor Showers and Their Parent Comets, which contains predictions about meteor showers in the next 50 years. So summing it up, he is who you should go to if you're interested in spending a night under the sky, figuring out stars, meteors, fireballs, and much more, especially if you find something unusual. We also have Ms. Siddha Ganju with us today. Ms. Siddha Ganju is a computer scientist and AI expert who works as a self-driving architect at NVIDIA. She also automated the CAMS network and also led the CAMS NASA Meteor Shower portal with Frontier Development Lab and Space ML. She is also the author of the book Practical Deep Learning for Cloud, Mobile, and Edge. Recently, she was also featured in the 30 under 30 list in Forbes. We also have a surprise guest with us today. Sahyadri is a BSMS 5th year student at IISER Tirupati. He has helped Ms. Siddha with the development of the NASA Meteor Shower portal. We will get to know about him more in the upcoming interview. Now, if you're wondering what CAMS is, both of them will also be talking a bit about it. If you have any questions in the upcoming session, please put them in the chat box and they'll be answered in the end. So without further ado, let us hear what they have for us. Over to you, Swastik.
Thanks, Amisha. So before we start, we are really glad to have you both for over here in the session. So we'll start, shall we? So my first question is to Peter. So could you tell us about what meteor showers are? I mean, like what they are and what's their origin and why they are important to study and overall how they affect our lives, the human lives.
Could I turn that question around? And I'm just very curious to see who else is on the Zoom call, who else is
sure.
listening in, and like to meet some of the people. It would be nice to hear what you know about meteors and meteor showers, and what sort of your interest is in astronomy. Can we hear from some volunteers who wanna give a little bit of background? Did any of you ever go out at night and on a reclining lawn chair, look up at the sky, look at the meteors?
Yeah, so I guess I'll go first maybe. Yeah, so in my first year, there was a. Okay, wait. Someone has raised a hand, so like let him go first then.
Good.
Yeah.
Hello.
I guess you're not audible, Begari.
Okay, now. Is this good now?
Yes.
Yeah.
Yeah, hi. So this is Siddha speaking from India. I'm currently doing my grade 10 and also interested in astronomy.
And did you ever see meteor showers or meteors or bright shooting stars?
Yeah, one recently in I guess it's in December 2020, we had one that was the first glimpse of a meteor I ever saw. It was a wonderful experience seeing it.
Was that during the Gemini meteor shower and around the 14th of December, 13th?
Yeah, yes, that's the same one.
Cool. Yeah, the Geminids are caused by a very interesting asteroid called 3200 Phaeton. And the Japanese are now working on a mission project where they want to send a satellite to this particular asteroid because it is causing all these meteors on Earth. And it looks, it's a really interesting object because most of our meteor showers come from comets, but this one seems to come from an asteroid, but a very frail, sort of primitive asteroid. And you can see that in the shooting stars because often with other meteors, you see lots of flares, at the end of the track, you see a flash, but the Geminids don't do that. They are stronger. So they move very, they glide through the sky, if you like, rather than having flashes and flares and being very irregular. So the Geminids is very interesting meteor shower.
Thank you so much for giving the opportunity, sir, and also.
Yeah, sure. Anybody else who has an personal experience?
Hello, am I audible? Hello, am I audible?
Yes.
Yeah.
Yes.
Yeah, we can hear you. Yes.
2 years ago, while I was traveling at night through a train, I witnessed a lone meteor. I was observing the constellations. At the time, I witnessed a lone meteor close a few yards next to the Orion constellation. I still have a doubt whether it's a meteor or a comet, but I'm happy that I witnessed one.
So the comet is the object that is in space and that travels around the sun. That's what we call a comet.
Made up of ice and ice and other dust.
Yeah, it contains volatiles and stuff that easily evaporates and sublimates. And so when the object comes closer to the sun, then those ices sublimate and they carry along dust particles, and that sort of make them fuzzy looking. So for astronomers, comets are things that are fuzzy.
Yeah.
And they're the planetary bodies, if you like. Usually they are about 1 kilometer in size. Comets don't tend to come small. They sort of start at a few hundred meters and then up. And then they can be very big. I mean, Comet Hale-Bopp was like 40 kilometers in size. So they can get big chunks. But that's a comet. And the meteor is the light phenomenon. It's the shooting star you see in the sky. So the bright light that happens when a little piece of the comet comes into the atmosphere.
So what
But
I
the
saw
question
was
then is,
meteor.
was this meteor that you saw, did it come from a comet or did it actually come from an asteroid? If it came from an asteroid, then its origin was somewhere in the asteroid belt, most likely. And in that case, it was stronger material, more stony or iron-like. And in that case, if it comes in slow enough, if it's big enough to start with, pieces can survive. And so, if you see one of those events, then it's worthwhile go look for it and see if you can find a piece. And now it turns out that that's very difficult. So finding meteorites is a real challenge. How big of a challenge? Well, over all of the Earth, every year, we are getting about between 10 and 15 or so accounts from people having seen a meteorite fall. Usually it's because it goes to the roof of some house or somebody sees it fall close to somebody. But it's that sort of number. And that number has been the same for almost all this century. And so there's now a little bit of an uptick because we're trying very hard to set up more cameras to catch them, but it's going very slowly. So we're still sort of in around the 14, 15, 16 of these falls a year over the whole Earth. And that's the number of cases that a meteorite is found. Meteorites fall very often. As a matter of fact, if you're running CAMS for a year, your chances that you will see one of these meteorite falls. But finding the meteorites, that's really incredibly difficult. But if it happens in your area, then you could organize a search effort, because CAMS does calculate very nice trajectories, and so you could potentially calculate where to go look.
Will it be rich in iron or uranium or other heavy elements or precious metals like gold, uranium, plutonium?
Yes. So if you want to know what a meteorite is made out of, then you basically want to just take a piece of the sun, just all the gas the sun is made out of. Take a big chunk of it and then let it cool down. And then everything that sort of solidifies, that's what your meteorite is, if you have a primitive meteorite. So it contains basically everything that the Earth and the planets are made out of, except there are meteorites that were not cooked and were not heated, and they stayed in sort of the primitive. They kept the primitive materials that form when you cool down things, and they basically contain some minerals that you don't find on the Earth. But that's because the Earth has been cooked and differentiated. We have an iron core and stuff floating on top, and so the chemistry is different. But all the elements are there, and meteorites were one of the objects that were used to sort of identify what is the abundance, the amount of what amount of materials are there when the solar system started.
Thank you.
Anybody else who has a story to tell?
Hello. Hello, am I audible? Yes. So one day I was watching TV and there was a window just on the left of the TV. So a minute or so, I saw something coming from space and just hitting, coming from space and then just vanishing. It was like a tail of tail or something, and it was like evening. So I guess that was a comet and not a meteorite, but that was a very beautiful moment for me.
So you were watching TV and then you saw bright light through
Yeah,
a
I
window.
saw yellowish or orangish light with a tail.
Okay. So we call these events fireballs, or bright meteors. And the yellow and the orange typically comes from iron in the rock, or from sodium. So sodium has this sort of orangey light. Usually it's a combination. There's some magnesium and all these things. But if it's dominated by the yellowish colors, then those, and then there's a component of atmosphere emission in there as well. But it's a bright fireball, and that again could be a meteorite fall. I mean, it could be that in that direction, somewhere on the ground, is a piece from space that
Correct. Even like when I knew about this, I woke for about 5 o'clock in the morning waiting for all the meteorites, but I could not see. I just saw one, or I guess I didn't see anything.
No,
But
it's
very
and it's
hard.
also very hard to go and know where to go look, because fireballs are surprisingly high in the sky, and so they are much further away than you think they are. They seem to be very nearby, but they tend to be rather far away. And so that's where a camera network comes in, because with cameras you basically film their path, and then you triangulate the trajectory, and then you get a track, and then that way you determine how it is moving in the atmosphere, and where something may have come down. Anybody else?
Good morning, sir. 5 years ago, when I was relaxing on my terrace, I just witnessed a comet. It lasted a second or two, and it just appeared like pale white in color with a yellow mixture. Yeah, that's my sighting.
Was it very swift moving, or was it slow?
Yeah, just very it was very fast actually. Yeah, yes. That's what I'm saying. It didn't last a second or two. I mean, I just witnessed it for a second.
This sounds more like a typical cometary meteoroid, so a meteor from a comet, and that it could have been that there was a meteor shower active that night when you were out. I don't know if that happened to be in August when the Perseids are there, or December when the Geminids are there. But there are actually many meteor showers every night, and one of the things we wanted to do with CAMS was to try and map out those meteor showers to figure out which ones are active. And so if you if this happens to you again, you see a meteor like that, and you sort of trace it on the sky between the stars and get a trace on it, then tracking it backwards should take you to the radiant. So like the picture on the back of my screen, that was taken during the 1998 Leonids. And so you see that all the meteors are coming from one point in the sky, which is called the radiant. And that's the direction from which these things are coming towards us. So you're standing sort of in the middle of it. And as you can see, they go left and right and above you, next to you. And so that's the direction from which the things are coming. If you now go on the CAMS website and you go to our visualization tool, that Siddha made a very nice upgrade from that, yeah. And then you can see which meteor showers are active, and what it shows is that direction. So it shows the position of the radiant. And so tracing it backwards should take you to one of these colored blobs that are on the map. Somebody would have to translate that for me.
Peter, do
And-
you want to talk about the Bennu one? I remember you talked about the mission that landed on asteroid Bennu.
Asteroid Bennu.
Yes.
So we did. The plan now is to try and observe meteors with a CAMS network in India, because we saw the success of expanding the CAMS coverage internationally from a project we did in 2019, where we put networks on the southern hemisphere. Asteroid Bennu is being visited by a NASA mission called OSIRIS-REx. The purpose of the mission is to study the asteroid and then collect a sample and bring that back home. And so that's what's going on at the moment. So in a couple of years, we hope to get a sample returned from this asteroid. So we actually have a piece in hand from an asteroid that is moving around in space, and that we can study by astronomical techniques. And this asteroid is in an orbit that comes closer and closer to Earth's orbit. Later this century, it's getting at its closest. And at the moment, the asteroid is still passing a little bit too wide for us to see meteors, but we weren't sure. And so we set out to go and see if we could actually see a meteor shower from this asteroid. Because normally, you know, with an asteroid, if you have an asteroid fireball, you see only one. So it's a very rare event. Meteor showers from comets are very rich. There's lots of bits and pieces thrown out. But asteroids is usually just, you know, there's a collision event and there's a relatively few pieces. In this case, the satellite was approaching the asteroid and it was discovering that the asteroid itself was active. It was ejecting particles. And we don't quite understand yet why that is, but the asteroid is creating its own meteorite stream. So it's not a lot of material that's being put out. And so we don't know if it's dense enough for us to actually see this, but it would be very interesting if we could. And because the stream gives us an indication of whether this activity we are seeing was just happening at that time, or whether it's something continuously, and whether the asteroid was more active in the past or not. And so, so we want to try and observe this meteor shower. And so that's why we set up all these camera networks in the southern hemisphere. And so this is an ongoing project. So collecting data, we'll do that for a couple more years, hopefully, and then see what we can find.
Sir, I have a little doubt, sir. Sir, have you seen Halley's Comet yet so far?
Yes. When I was at university, I was studying astronomy, and you know, one day I was late at the university, and I was waiting for the elevator to go up, and a person was there. We got into talking, and he said that he was organizing an airborne observing campaign to look at Comet Halley. So he was approached by a company that had chartered an aircraft, and they were going to bring people up above the clouds, because this was in the Netherlands, and so it's very cloudy there, above the clouds, and they were going to give people an opportunity to see Comet Halley. This was back in, when was it? Long time ago.
76, I think.
Yeah, long time ago. So in any case,
sorry, 86.
86. That is about right. So so yeah, so that was you know, a very interesting activity, but they needed some experts. They needed some people to come along and be the, you know, the guide. And I volunteered, of course, immediately. Said, oh yeah, cool. So me and another person got to go up with this aircraft, which was like a DC-9 or some that's a smaller sort of regular commercial aircraft. And we flew over the clouds, and we did little 10-minute lapses, and everybody, you know, was expecting this big, sparkling, bright, fantastic comet in the sky, but the object was only magnitude +4. And so it was really hard to see. And so the first time we did 2 of these flights, and the first flight we did was a mess. Everybody disappointed, and I really didn't know what to do. And the second time we said, guys, stay in your seats, help the person on the window with his or her binoculars, and allow, help them find the comet. It was in the constellation of Capricorn, so we had to point out where constellation of Capricorn was, and so that people could see the comet. And in the end, about 1/3 of the people actually were able to see the comet. So it was that difficult, but it was quite an experience. And one of the persons I spoke with just couldn't. She was old, and she had, some problems with her eyesight. And looking through her binoculars, through an aircraft window and so on, was just a bit too much asked. And so I sat with her for a little while to just, give her company. And she told me that she really wanted to see Comet Halley because as a child, she had seen Comet Halley. And so this was the next return of the comet. She had seen the previous return of the comet back in 1910. So this was for me, incredible experience just to hear her talk about it as a kid, how her dad took her out and they went out and saw this. So yeah, that's a comet. It's a fuzzy object in the sky, and it very slowly, from day to day moves between the stars, and you can track it. Astronomers measure positions of it, and that way they sort of track the orbit of the comet around the sun.
Yeah, I remember last year while trying to spot the Neowise, the struggles to spot that.
Yes. Well, Neowise was so bright that you could see it with the naked eye, but in binoculars, it's usually a lot nicer. So if you have binoculars, definitely bring those along. Comet Hill Bob, I don't know if people remember that one. That was really nice.
I have a doubt here. Is the comet, is it possible for a comet to self-disintegrate if there's some suitable thermodynamic conditions persuade there?
Yeah, so that's an interesting question, because one of the things we learned from studying meteor showers is that even in the inner solar system, disintegration, fragmentation, falling apart, losing big chunks, whatever you call it, is the main way in which comets lose mass. So it's not the fuzzy structure of the sort of the yearly coming back. If you add it all up, it's really there's moments in the life of a comet where there's big chunks being lost. And you could see that a little bit in the case of Rosetta, for example, when the Rosetta mission went to Comet Gerasimenko GC. The comet looked like it was an onion, like actually 2 onions top of each other, and so they were sort of layered. So people are thinking that when comets formed, they probably just were very fluffy, very loose material that pluffed into each other, and then the thing that would impact would basically completely fall apart into debris, and that debris would rain down on the object, and that way over time you would build up all these layers. And so if you look at the onion of Rosetta's comet, you can see that there's big chunks bitten out of it. So this comet also at some point in the past lost chunks of it. And comet fragmentation is a process that's really hard to study by a satellite, because it happens rarely, and so it's not one of these things that you can study in detail. But we see it very often with comets, that when you see a comet pass through the solar system, that chunks are coming off. And turns out
or is this phenomena is captured in our systems of photography? I don't know where it is captured.
It's captured in the topography of the Rosetta comet, I think.
Comet disintegration itself.
Yeah, but it's also there is great observations of a couple of comets that that were very well imaged, like Comet Linear a couple of years ago, as a long period comet that came in that fell completely apart. And there was a recent case in 1995 when Comet Schwarzmann-Wachmann broke up very spectacularly so. And Schwarzmann-Wachmann is actually a parent body of one of our meteor showers. That means that the comet orbit passes very close to Earth's orbit. And so in 2022, so next year, there is a small chance that we see some of the debris of that event from the breakup of 1995. The calculations show that it passes just outside of Earth's orbit, so maybe we won't see anything. But there is a big interest in that case because it's linked to that fragmentation. It's not clear that we've seen meteor showers that are definitely from a recent breakup. Like, for example, very famous shower is the Andromedes from the 19th century. Also, let's see, seen in England in one year, and the other year, I think it was in the US. Big, massive storms, really large numbers of meteors for a few hours, spectacular event. And that happened a few years after Comet Biela was seen broken up and was subsequently lost. And so the thinking was that what we were seeing with Andromedes was the debris from Comet Biela completely disintegrating. But I'm not convinced that's true, because if you make the calculations, you can show that the debris from the breakup actually wasn't near Earth's orbit. So what we were seeing was the activity from the fragments that continue to be active. So we're seeing the results of individual dust trails, not of that breakup, we think. So so yeah, the meteor showers, if the timing is unfortunate, they can be very, very intense.
So you mentioned the name CAMS like quite a few times. Yeah, so like you started in 2009, right? The CAMS network. So did that have to do something with the 2008 recovery of the Comet TC3, or?
The name CAMS?
No,
CAMS is based.
Not CAMS. Not CAMS,
yeah.
like the network or the project.
Yeah.
Yeah.
So the CAMS, the name was based. It's based on the fact that we're using surveillance cameras. It's really a surveillance camera based system. That's how we are filming the sky and we are mapping the meteor showers. The reason for CAMS that we started this project had to do with me personally. I wrote this book in the back here, Meteor Showers and Apparent Comets. It's sort of an overview of our field, which after the Leonid meteor storms, I felt that we needed a summary of what we knew at that point about meteor storms and unusual meteor showers and so on. And the most difficult thing to write for that whole book, would cost me more time than everything else, was a table on which meteor showers exist, because from the literature back in 2006, the literature was so opaque. It was so difficult to understand what was really observed and what wasn't, what was known and what wasn't, what was known and what was suspected, and so on. So that it was a morass. So there was like, for example, the Draconids, the October Draconids, a shower caused by Comet Giacobini-Zinner. That shower was known by 8 different names, if I recall. So and so we needed a better way of mapping out our meteor showers in the sky. And that was really what video cameras made possible in those years. It was really a tool that started to make it possible to map out the meteor showers.
And how does AI come in help here? I mean, like, Yeah. Like, what's the reason to bring up AI in this point in this project? Like, how does it help in the project?
This is a question for Siddha, so she should answer this. But my part of my background is, in this case, is that SETI Institute was organizing a frontier developments lab where we were trying to find projects where AI could be used, could be helpful. And I, as an observer, was literally staring at every meteor triangulation. So every set of data from a shooting star that we had, I was looking at a computer screen to verify that it was real or not. And I've done that until the end of 2016, and I was so completely fed up with it at that time. I mean, you know, I'm committed, but not there's a limit. That we needed to do something else. And it was clearly that the project was going to come to an end if we didn't find a better way. And Siddha's team, the whole team of people, stepped in and found that better way.
Yeah, so as Peter was saying, you know, he used to basically day in and day out sit through what we like to call as, you know, these moments of darkness and just wait for the video stream to show up and wait for the meteors to actually show up in the video stream. And the team in FTL, we realized that this is a process that we know can be learned by a machine learning algorithm, because we've seen that computer vision, detection and recognition machine learning algorithms are quite good at it, especially if trained on a good enough data set. And, you know, Peter had been creating that data set, curated data set for us from 2010 to 16. So it was almost a win-win. You know, we could train a really good machine learning algorithm that could replicate, you know, the understanding of what really a meteor looks like. And that really started from making sure that the data aggregation algorithm, which means that collecting data to the central location at the SETI Institute. So all the different CAMS stations, data is coming in from all those different CAMS stations to the SETI Institute and is being analyzed at that central server. And then on top of that, train some sort of a machine learning model that really replicates Peter's thought process and is able to identify, okay, this looks like a meteor or this does not look like a meteor, right? And then, you know, Peter used to always talk about, you know, we need to figure out what, you know, we see all these meteors every single night, but we need to really map them out on the globe. And that's how the very first meteor shower portal, and the second version of that is what you see behind me, that really came out. So every single point or dot that you actually see on this globe is something that the CAMS network has detected and has verified as a plausible meteor. And I think that, you know, back then in 2017, having a path to deploy AI, I think that was really revolutionary in CAMS itself. And, you know, that's one of the major reasons why I think we were able to succeed and deploy this pipeline. And we are improving it every year now.
Yeah, and like
it's really an evolution.
Yeah. And you know, Shayadri from this very institute, he's actually helping build this very improve this very portal. He's been working on identifying constellations. Well, not identifying constellations, but improving the rendering process and the creation of constellations. So it's you know, we are a team and everybody's doing their bit. So that's awesome.
Yeah, the reason I asked each of you to tell a little bit of your own story about watching meteor showers is because there is a really big step from your own experiences, you know, going out and seeing a shooting star in the sky, to a visual presentation like you see behind Siddha there. I mean, to really appreciate the value of that display, the fact that you actually can see where the meteor showers are, which meteor showers are active, and you know where the meteors are coming from, and so on. that requires some understanding, some knowledge, and a lot of the improvements is really to help make that site more accessible, so that it's really being used. The people who enjoy going out to look at the stars, look for shooting stars, that they actually can use this as a way to understand what sort of showers might be active tonight.
I guess you.
Hello? Hello?
Yes, I can hear you,
You
Joey.
can go ahead. You can go ahead.
My name is Nurali Jiwaji. I'm from Tanzania, Dar es Salaam. I don't know if I'm in the right meeting, but I see that most people are here from India. I'm in a group, in an astronomy group, mainly from India. But I am interested in understanding whether this all sky camera network is distributed across the world, or is it only in particular parts of the world?
So there's different efforts going on to try and set up more cameras. So our main goal is to try and map meteor showers, and so you don't need to cover the whole Earth for that. You just need to have good longitudinal coverage, so that you have observing sites at all places on the Earth where it's clear, and each site covers maybe 100 by 200 kilometers or so. But for meteorite falls, you really do need to have all sky cameras, and so there are also groups setting up more all sky cameras in the world, and usually it boils down to buying the cameras and running them. With CAMS, we have a lot more. With Fireball or sky cameras, it's one fireball a week or so, or one fireball a month. With CAMS, it's 100 to 300 meteors a night, so you need a lot more processing of data, and so that's more organized. But you could in Tanzania, you could decide to set up your own network, even a CAMS network if you like. If you have a partner at about between sort of 40 and 110 kilometers away from you that also wants to do this. So because it's a triangulation system, so you need to look at the meteors from two places at least. 3 is better. And then you can set up a camera and PC and run network. To have really good sky coverage, to have many meteors, you need a lot of cameras. So it becomes a real project.
Okay, so can you share some links where I can get some more information about?
I think Swastik will do that later.
I'll put them in the chat box.
Okay, thank you very much.
It's nice to hear you're from Tanzania. I have visited Sudan on occasion because in 2008 we had a very interesting case where an asteroid was seen in space. It was tracked for 20 hours, and that asteroid impacted the north of Sudan over the Nubian desert. And at the time, the impact was seen from space by US government satellites as a big flash. And we knew from that observation that the breakup, the flash was very high in the atmosphere, was 37 kilometers high. And nobody had ever found meteorites from something breaking up that high. It means it's fragile. But I was not so convinced. I wanted to try, and so I teamed up with Mawiya Shadat at the University of Khartoum. Traveled there, and about a few weeks after the fall, Mawiya was an incredible organizer, and so he brought together a large group of students and staff from the University of Khartoum, and really a busload full. And drove 10 hours north from Khartoum to that spot in the Nubian desert close to a train station called Station 6. And from there we started, first we just asked people, and we asked a station attendant, and he was telling us that he was woken up by the light. It was that bright. And, you know, he was sleeping on his veranda there, and he was woken up by the light, and he saw a big flash, but he didn't really see things coming out of the flash. So this sort of was consistent with the idea that everything just goes into dust rather than having meteorites survive. So, you know, I wasn't so convinced we were going to find something, but here was a bus with students, and so we, you know, had to try. So we drove 28 kilometers into the desert, had to create our own road, and then lined everybody up in a long line in the area where I thought we might find something, and started walking. And it took only 2 hours for Mohammed Alamin, who was a geology student at the time, to find the first piece. And and after that, we found 600 more in 5 or 6 observing campaigns. And that proved to be one of the most interesting meteorite falls ever, because it was a very rare meteorite type. It was a ureilite, and it was also a mix of things. It was a polymicted ureilite with mixed in a variety of other meteorite types. And so from that fall, we learned that if you have a meteorite fall, if there is a fireball, and you find a piece of it, then don't stop with that. I mean, keep looking, because if you keep looking, you may find other things. You really need to find, give yourself a good, complete picture of what came down. It's maybe not important if you only had a 10 centimeter big rock coming in, but if the rock was as big as TC3, which was about 6 meters, then you definitely do want to, you know, keep looking. And that's what we did. And so we learned a lot about ureilites, polymicted ureilite, the history of the planet where this material originated. It's a really strange story, because it was an object that formed in the same areas as the Earth and Mars, the inner planetary system. It experienced a very violent collision during that time that almost broke it apart completely. And it got sorry, before it experienced that collision, the thing had already become pretty hot, because there's all these radioactive elements in there originally, and they heat up the material just like the center of the Earth is heated up. And so this thing was already getting pretty hot, but not quite so hot that everything melted. So it did not differentiate. So this thing did not have an iron core. But some of the minerals flowed away, and but the main minerals, the olivines, pyroxenes, and so on, stayed in solid form. And then it experienced the collision. And then all the pieces that came out of that somehow reaccumulated and built back this now big jumble of rocks. And then somehow that thing made it into the asteroid belt and survived the formation of the terrestrial planets, and is a very unique object that is now found there. So all these meteorites tell us a story about, you know, the asteroids that formed at the time of the formation of the planets.
Yeah, I guess Professor, I guess there are 2 more hands that are raised. I'll just first ask Professor Jesse.
Yeah, hi Peter. I have a quick question. Like, once you identify the meteors through CAMS network, what is the next step to study them more about their physical parameters? What are the next steps for that?
So there's a bunch of things you can do. One of the most interesting thing I think is the question of age. So you can, once a meteorite stream is well described, even if you don't know the parent body, you can do simulations that show the formation of the meteorite stream and how it evolves in the planetary system. And we have 400 or 500 meteor streams now, and only a handful we have any inkling on how old they are. And so there is a lot of information to be had by just trying to figure out from the spread of the material and maybe the spread relative to the parent body, if you can identify the parent body, how that material, when that material was released and how long it's been around. And then all these comets are sort of little time capsules. They tell you about the history of the solar system going back thousands, tens of thousands, maybe 100,000 of years, to sort of describe how comets, how many comets there were in a solar system over time, and how they fell apart over time, and so on. So that's the record that is being kept by this meteor streams.
Yeah.
And
So
of course, yeah. And the modeling itself is interesting also for predictive work, and a bunch of that has been done because satellite operators are very interested in that. The satellites in space are being exposed to these meteorites, and if you have a dense stream, then you want to know about it. You want to know where it is, and so so there are models being created from if you know parent body, or if you have seen a meteor storm in the past, you can make predictions about when it might return. And this is all, you have to do this carefully. You can't, shortcuts won't work. So taking mercury out of your dynamics calculations, for example, will throw you off completely. It's that sensitive. So you have to do it well, but if you do, then you can make predictions on what to expect. And so the effort, there's a big effort at the moment to try and understand this breakup of Schwarzmann-Wachmann tree and see what that might do next year when we have an encounter with that dust.
Okay. So other than that, is there any attempt for more focused observations, kind of, or is it possible?
To do custom observations. So the reason why we think it's a good idea to have a network in India is because there's basically no good coverage from the United Arab Emirates. There is some observations in Japan, and then it's California. So it's really, on the Northern Hemisphere, it's really, very poorly covered. And that means that if you are on regular operations of CAMS, it's a surveillance system. So once it's running, it's a pain to set up, but once it's operational, it runs fairly easily and keeps collecting data every night. And then once in a while, you pick up something unusual. And then suddenly, there's a whole set of new questions coming up. So for example, a couple of days ago, 9 to 14th of June, we had a new meteor shower show up of a complex called the June Aqueducts. We know very little about the June Aqueducts. We know it's a very rich shower. There's a lot of meteors detected by radar as well as by video cameras, but we don't know the evolution. It's a sun grazer or sun skirter type of comet where I think there's one sun grazer comet that Soho saw that could be parent body, but there is no closed orbit of that object. And so so we know little about it, but then between June 9 and 13 this year, suddenly we saw a whole bunch of meteors coming from a new component in that shower. It wasn't completely new because I noticed it the year before, but at the time we had mislabeled it, and so we thought it was normal return. But it wasn't, something new. And so then the question immediately comes on, okay, why is it there? And what does it tell you about, potentially dangerous comet that might be out there? Or what does it tell you about the evolution of this whole June Aqueduct complex? And what is the history behind that whole complex? And it's an important complex because it has all these small particles in it, so it contributes to the satellite impact hazard. And so the special projects, I think that those are very interesting. If India picks up something that other networks don't see or not as well, then you could focus on that. But there's so much effort that can be done. I mean, there's so many projects you can think of that could be interesting. The light curves of the meteors could be interesting to look at. The physical properties, like I was describing, the Geminids look different than other meteor showers look. There's a lot of potentially a lot of work there that can be explored.
Thanks.
Yeah, so there is another hand. So GBRK5, I don't know what his name is.
Sir, am I audible, sir?
Yes.
I have a question which is personal to your institute. Can I ask? Since you're from SETI Institute, which stands for Search for Extraterrestrial Intelligence,
yes, it is.
Do you use, is it possible to use CAMS network to identify otherworldly extraterrestrial crafts?
Probably. Okay, so
by that I mean
it's an interesting question, and we are sort of thinking about that. CAMS is designed to track meteors, and so it has software built in that sort of select the meteors, and that's very much what Siddha's deep learning tools do. They recognize meteors from non-meteors. So everything in the non-meteor group, you know, gets tossed out. That doesn't mean it's not interesting. And so the monitoring other things than meteors is possible if it's high up in the atmosphere. If it's low in the atmosphere, then you need a very dense network. So it becomes very difficult. But if it's high in the atmosphere, like where we are looking at meteors, that's sort of above, say, 40 kilometers, from 40 to 120 kilometers. And if it's that high up in the atmosphere, then a network like CAMS would, if it's light, bright, and so on, then it would see things.
Okay, sir. So you mean if we can find the UFO in stratosphere, we can track it using CAMS?
Well, it depends. It has to emit light, and it has to be in nighttime, and you know, all those things. And if it moves in a zigzaggy way, then Siddha's tools will throw it out. But it's like, it's a video surveillance camera system. So what you can see with video surveillance cameras, you could potentially set up observations doing that. We already, we are very interested in fireballs and the meteorite falls. And we are already using people's cell phones and so on, you know, the videos that you capture with those to track meteorite falls. And so when there is a meteorite fall, even when it's not in the CAMS network, it is worthwhile to collect the different videos that, you know, other video security camera systems pick up.
Yeah, so I have heard about a project that uses cameras to detect exoplanets. I forgot the name of it, but then there are a few projects like that too. Yeah, so Siddha, you were talking about the uploaded version of the NASA Meteor portal, right? Like so. So like my next question is to Sahyadri. So if he's here, is he here?
Yeah, I'm here. Hi.
Yeah, hi Sahyadri. So my next question is like, how was the experience? You know, working on the project, and you know. And then what exactly did you do during that period? Or are you doing during this period?
So before I say anything about that, I want to thank Siddha for mentoring me through the whole process. I was really honored to be part of this whole project, and also Dr. Peter for answering some silly doubts that I had over mail about the project. So thank you so much to both of those guys for that. Initially, I was working on the web page and the UI that you can see in Siddha's background. So my task was to create the constellations that you might see in the visualization. And as Dr. Peter mentioned, it was to kind of correlate what you see what you see in the visualization with what you might see in the night sky, to make it easier for any person who might use that visualization to figure out where the meteor showers are coming from. So my task was to use Python to create essentially a script that would generate the constellations for each day that the visualization services, and it makes small adjustments to the constellations with each day, so that it makes it easier to find the meteors. And along with that, I'm also working currently on building a pipeline to correct the various machine learning tools that Siddha has made that will help detect the meteors. So there's already a script that has been made, and I'm kind of helping optimize a few things and clean up the script a little bit so that it runs a bit smoother. And along the way, I've learned a lot of things. So first of all, there's a lot of cool work being done, not just in the CAMS network, but overall by NASA FDL. And I've had the chance to attend a few seminars where they showcase their work. And being a science student, it was really enlightening to see how all of the, so for example, when I've worked on different projects, I've had to use tools that make it easier to access certain data, and to see how the various AI experts construct those tools. And it's really interesting because you never get to see that, you never get to have that insight into how all of those tools are made, because that's directly contributes to how much easier it becomes to do science later on. So, and also I've gotten to meet and talk to a lot of talented people who do a lot of cool work. So not just, so for example, in the UI, I've never actually built web pages or done any of that thing before. So meeting people who have done that sort of work also was really cool. And then obviously meeting Siddha and talking to Dr. Peter is in itself an experience, because they're experts at what they do. And for me personally, it was also interesting because I started my journey in programming only in the second year of university. So I hadn't really dealt with any programming languages before. So it's been cool for me to, it's made me think, this whole project has made me think a lot more like a programmer, and to, weigh a lot of things, the importance of a lot of things while writing programs, such as the readability of the script, the, how fast a certain code works. And it's also been a sort of an output for creativity as much as, say, an artist might find in their canvas, because I'm not the most creative person when it comes to drawing or anything like that. So I suppose programming is a little bit of a creative output for me.
Yes, should be. Cool. Yeah, it was very nice to see this come together and actually see the constellations.
I think we lost your audio.
Yeah.
Okay, I think I lost audio for a minute.
Sorry.
Yeah. Yeah, so Peter and Siddha, so now that the network is set up and it's expanding, so what do you think will be the future for the CAMS network? How, what do you think about that?
So if you can still hear me.
Lost you again.
Yeah? Okay. Yeah, good. So I think that I would like to see CAMS continue for if possible many years. The technology will evolve and will get better. Hopefully it becomes easier to do. But I'm hoping that this type of data will be collected on a global scale for many years to come, because we've been doing it on a global scale, only sort of global, for only 1 or 2 years now, and we are seeing like every month there is something unusual happening in the sky, and that's very cool. So I'm thinking that it's those unusual showers, the strange, like the thing that happened in the middle of June, those are will continue to be interesting and exciting, and there's information there that we can't get in any other way. And so I think that it's also fun for the public because these unusual showers are, interesting to watch, to go out for. And if we see a shower and we spot it with the video cameras, we can warn people and say, look, there's something happening. Go out tonight if you can. And we're getting better at recognizing them quickly and getting announcements out and letting people know that something unusual is happening. The more points on the map, if you look behind Siddha at our map, it looks very nice. You see these yellow and orange and blue blobs and so on. Yeah. Okay, so those are our meteor showers. But the reality is that if you would have 100 times more points on this map, then you would see a lot more meteor showers. There is potentially a lot more detail there. I'm certain of it. And that means that, if we can make much more detailed map, if we get many more measurements made, then that's going to be opening up a new way of looking at the universe around us. We'll see all the things. So we'll see, unusual things like, for example, long period comets. They're potentially dangerous, like Comet Hale-Bopp, can be big. You don't get warning, you just come right at you if there is one. These long period comets, if they get too long, then the meteor shower gets too much diluted. So it gets spread out over too much, too much of an orbit for us to detect. But if you keep observing the meteors, then, you're building up statistics. And at some point you will start seeing more of these events. And you may get a better understanding on what comets are out there that still need to be found.
And like a few years ago, we had spotted the interstellar comet, right? The Oumuamua comet. So like, can CAMS be helpful in like these kind of objects, like spotting them or like finding the dangerous of them?
We're not finding the asteroids because those are really faint, and our cameras are not bright enough to see that. But if there are interstellar meteoroids that move very fast and that hit Earth's atmosphere, then potentially you could detect those. The difficulty is to have your techniques be so good that you can be certain about these fast speeds. And so it will require some evolution of the technology to really get to a point where things are very precise and very reliable.
So Amisha has raised a hand. You can go on.
And natuurlijk make sure that Siddha's filters are not throwing them out.
Yeah, we would need to train. We would need to train on the data. Yeah.
Yep.
Hello, sir. So I would like to ask a question with regards to an article I read, and it was about a 2019 meteorite fall in Costa Rica, I guess. They were called as Aguas Zarcas or something like that.
Yes.
And they were a type called carbonaceous chondrite. So, and that they held a lot of evidence for amino acids and things like that. So what is the possibility? I mean, what is the further steps you take to determine whether, if there is life or anything closely related to that in the extraterrestrial systems?
So I don't think you would necessarily expect life in meteorites themselves, because meteorites are formed in not in a liquid water type environment. So you don't have the sort of conditions for life to originate. The thinking is more that the meteorites may be representative for asteroids that hit us at the origin of the Earth, when the Earth was formed, and that these objects brought with them organic compounds, because when the Earth was formed, it was a very dry place here, and it was a very organic, poor place. And so the water we have and the water and the organics you and I are made out of came from objects that were much richer in it. And it could have been comets. The isotopic evidence goes towards more primitive asteroids. And so then you're thinking, okay, Aqueducts, primitive carbonaceous chondrites like that. Those are very interesting. And so, so when there is a carbonaceous chondrite fall, then there is usually extra interest in trying to get a pristine sample. So if ever one falls near your house, try and collect it quickly before rain hits the area, which is hard, and keep the sample free from human contamination, which is even harder. So so you want to preserve it very well. And with Aqueducts, there are already many studies done on that meteorite. So when there is a meteorite fall for which the meteorite is actually found, somebody finds a rock, and there is video information from CAMS or from other video security camera systems and so on, we do try to encourage or organize ourselves projects where you really go in depth in studying the trajectory, the orbit, the origin orbit on which it comes in, and the properties of the meteorite. Because the meteorite, when it, so we basically want to know from where in the asteroid belt are all these meteorites coming from. So Aqueducts, where did it originate? It was somewhere in the asteroid belt. This was a CM class meteorite. We happen to have two cases before where we had CM type meteorites, and we saw it with video cameras, photographic cameras. And that was Sutter's Mill in California, here in the backyard, just 3-hour drive from where I live, and the Maribo fall in Denmark. And for those two meteorites came in on very eccentric orbits with an orbital period that was similar to the 3-to-1 mean motion resonance with Jupiter. So the orbital period tells you from what resonance the meteorite is coming, because it's the resonances in the asteroid belt that change the orbits. So initially the orbit sort of goes almost circular, you know, little eccentric, almost circular going around the sun. And then the orbital period grows a little bigger or smaller and ends up in one of these resonances where the asteroid goes around 3 times when Jupiter goes around once. That sort of situation is unstable because suddenly the asteroid feels the pull coming from certain directions in the sky, and instead of sort of being randomly distributed. And what that does is it makes the orbit more elongated. It moves the one point closer to the sun, the perihelion, and moves the other point further out. So the orbital period stays the same. But the result is that if the outward going part doesn't hit Jupiter's orbit, because Jupiter is really good at kicking everything out of the solar system. So if it stays close enough in, while the inner part comes in and comes close to the orbit of the Earth, then you can get a meteorite fall. And that we saw with Sutter's Mill and Maribo, and it was really sort of this nice, fresh, elongated orbit coming out of the asteroid belt. There were very few interactions with the terrestrial planets, so it was still you could still see it come out of the belt. And you can also tell from the steepness on how steep it sits on the plane of the planets, of how high in the asteroid belt the origin source is. So we're playing those tricks to try and figure out from where in asteroid belt our meteorites are coming. In very rare cases, we had just recently published the results from a meteorite fall in Botswana. That was found in the Central Kalahari Game Reserve. And that was also an asteroid that was seen coming in. There's asteroid 2018 LA. That one had big flare, was over a really difficult to get to area. But with the local authorities in Botswana, we were able to organize a search campaign and found pieces of it. And those pieces turned out to be of a type called HEDs, Howardite eucrites diogenites. which come from asteroid Vesta, at least certain types of it. And so what you do in that case is you study the meteorite for its isotopes to make certain that it comes from Vesta. That's not one of these anomalies, because there's also other ones. And you study how long was the rock in space. So when it gets excavated, then the rock spends as this one was 1.5 meters in size. It spends like that sort of a rock in space. During that time, it's bombarded by cosmic rays, by fast neutrons, for example. They start nuclear reactions in your rock. They change the elements, and they can go from magnesium to neon, for example, the noble gases. And then the neon creates slow neutrons, and the slow neutrons can get other reactions. So you get a whole slew of different strange isotopes. You can detect those, and from that you can tell how long this rock was in space. And so we knew that this particular rock was in space for about 23 million years. And turns out that 1/3 of all our HEDs are from this collision event, 1 or 2 collision events that happened 22 or so million years ago. And so then we knew, okay, it belonged to that one. We then looked at the maps of Vesta. The NASA sent a mission to Vesta called Dawn, and they imaged all the craters. And in those maps, you see craters that are fresh, that have an ejecta blanket. You can see it from the slightly different composition of the rocks, and you can see it in the shape as well, sort of like a aura of rubble around it. So when that happens, when an impact happens and it creates that ejecta blanket, it makes a fresh new surface. And that fresh surface is bombarded by small collisions. And by counting the small craters, you can figure out how old the crater is. You know, it's very old, it has lots of craters on it. It's very young, it has very few craters on it. So the difficulty is that we don't quite know how many impactors there are, sort of the meter to 10 meter size. So that's a bit of a debate. There's 2 chronology schemes. It turns out that in one chronology scheme, our technique doesn't work. In the other chronology scheme, it does, and it fits very nicely to the cosmic ray exposure ages. And so we looked at the craters, and it turns out there's very few candidate craters that where this stuff could have come from. There was actually 2. And it turns out that the 2 craters are found in very different terrains on Vesta. One is on a slope, on the slope of the Big Rhea Sylvia impact basin, and the other sits on a topographic high on the ridges, and the Vena Fossa ridges. And so by looking at the meteorite and studying the properties of the meteorite, we saw that this meteorite had no solar wind implanted noble gases, meaning that there was no turnover of the soil. And so there were no landslides. That's our thinking. And so we are thinking that the thing in Botswana came from the crater that sits on top of the hill. And so that's how we figured out, you know, where that particular meteorite came from. But that was thanks to the fact that we had imaging of Vesta, and because Vesta is a really big asteroid, and chances that if you know something comes from that type of meteorite, chances are it comes from Vesta and not from its family of smaller asteroids that Vesta has, called the Vesta family. So it really has to come from, chances are it comes from Vesta. So the study for the Aqueducts meteorite is still ongoing. So we're still trying to improve that, and we're still doing measurements and still trying to figure out what the exposure times were and all those things, all those little pieces of the puzzle that we need to make that into a good story. But if it ever happens in your area, if you find a meteorite and you have video imaging of it, you have a track, then we can try and do that the same thing. And get everybody involved, everybody who wants to look at the rock, try and learn as much about it as possible, and then figure out when, from what collision event this originated, and then look at the orbits and then compare it with other orbits and try and see if we can figure out, you know, from what asteroid it came or from what debris field in the asteroid belt it came.
That's pretty cool. I obviously don't know the intricacies, but that sounds amazing.
these are always meteorite falls are always really cool stories, you know.
Yeah.
Just
Yeah.
the circumstances, and it's always keep in mind when you talk with you know, other students or the public that meteors is usually something that is the people's best experience, that the universe around us is moving. We're really in a space as a planet, and you see that by just the stuff coming in the atmosphere.
Yeah. It's our own backyard.
Yeah.
Yeah. So are there any other questions from the audience we have here? Has anyone to ask anything? Can I just have a quick question? Okay, like how does this, you know, studying these meteor can, you know, can tell us about the history of our solar system, like the formation and the evolution about that?
So depends what you're looking at. Meteorites have played an enormous important role in our understanding of formation of the solar system, because with meteorites we have the most primitive samples of our solar system. If you have a meteorite in hand, it's the oldest rock on Earth. There's nothing on Earth that is, you know, as old as this meteorite. That's true for most meteorite types. And so, so meteorites are really, really precious samples from early times, and they contain little capsules, little grains, bits of material that go even further back from that sort of give you an impression on the environment in which the solar system formed, the supernova, the old stars, and so on, that contributed to dust and the debris that made our solar system. And so meteorites are, in that respect, really important. With meteoroids and meteor showers is a more recent example. So what we are seeing is doesn't survive that long. The oldest meteor showers we have, you know, are maybe 1 million years old, but not much older. And so what you're seeing is basically the over that 1 million years, the evolution of the primitive objects coming into the solar system, the comets, the influx of Oort cloud comets, the influx of objects coming from the Kuiper belt. And those are also remnants from the origin of the solar system. So people are really trying to figure out, you know, what is out there. The Oort cloud per se has never been really seen. I mean, we now have comets moving in it that really look Oort cloudy-ish, but you know, as such, the Oort cloud is still a bit of an enigma. The Kuiper belt is now better observed, and we're gradually getting more and more insight into what that is. There's of course other objects out there as well that play a role in the dynamics of all these objects, and so yeah, so there's a whole well, one of the things that I was interested in, and I worked on with David Nesvony at one point, was, you know, where does our zodiacal light come from? So you see, if you go out at night, you see this sort of Milky Way, the false Milky Way, this other band of light that is caused by dust particles in our solar system scattering the sunlight. And what are these dust particles? What is the cause of that? And so at the time, the scientific discussion was going towards asteroids. People was pushing it towards, oh no, this is all asteroidal dust, because, you know, otherwise we can't explain the zodiacal dust bands and so on. But I think now the pendulum has swung back to us thinking that, you know, 90% or more of it is from comets. So comets are really the main source. And we're also starting to get better idea on that it's really the breakup of comets, fragmentation events, and so on that are causing the biggest influx of dust. But yeah, so those things you learn from everything that doesn't belong to a shower, you know, the sporadics, the old stuff. How does it survive? I mean, how do dust particles survive the solar system? How do they age? Very important question. Why are meteor showers not older than 1 million years? Why are some meteor showers not older than 100 years? Why do they fade? What are the processes going on? Same questions people ask with asteroids. I mean, asteroids coming in the solar system. If you have the very primitive ones like Aqueducts, they also seem to fall apart. You seem to also have processes undergoing that make them, smaller over time. So those are that's sort of the big picture.
So I think we'll take one last question. It's from Zeel Jain. Can you ask the question? Like she's.
Hello. Yeah, so my question was that when was the first time you saw a meteor shower, like in your childhood or when you grew up? When did you saw it? And I also have a question that how has CAMS made your work easier? Like how much has it made your work easier? The AI and all.
So the origin story I like to tell. I did go out, as a kid and watch the Perseids, but I became a member of the Dutch Meteor Society. At least I met people from the Dutch Meteor Society when I was a student, just like you guys are. You got introduced in something, and I got introduced into observing meteors. There was a person called Hans Bedlam in the Netherlands who was organizing triangulation of fireballs with photographic cameras. There's photographic cameras in those days. Developing films, it's looking at it's an incredible amount of work. But in any case, that was the project, and I asked if I could help. And so as a student, I think in my first year, I spent an hour and a half on the balcony of my apartment in the city of Leiden, which is light polluted, very bad conditions, looking for an hour and a half for meteors, just watching the sky. And I managed to do this for an hour and a half. And in the end, I had four tracks drawn on a star chart. So I saw 4 meteors in an hour and a half, which is not bad given the fact that, you could barely see the stars in Leiden. But I think, it wasn't a big spectacular shower that sort of took my breath away. It was just sort of this hope of seeing something that sort of got me hooked, I think. You always wish to see one more. And that really, that made it fun for me. And so I spent, from that moment on, many years just watching the meteors with the naked eye. I was organizing the Dutch Meteor Society visual section, helped to basically also monitor meteor showers to understand what sort of meteor showers were active. But at some point, the technique of doing this visually is very limited in terms of the certainty you have and where the gradient is and so on. And so we got sort of stuck there, and then the video cameras came around, and that really made that whole game possible, because now suddenly, you had records and you could make calculations and you could get the actual direction determined precisely. And then with the AI, as I said, I mean, it just we hit a wall at some point. So that we had to automate. It was basically the automation that made things. And now the task is different. So now I'm more focused on having more networks in the world, and maintaining the networks, making sure that asking people to reboot their camera, reboot their PC. Or if somebody bumps a camera that's out of focus, to refocus the camera, that sort of thing. Then to actually have to look at every meteor and check every triangulation, which is fun doing, but not not if you have to do this, if it becomes a job. And the difference has also been that before Siddha's project, we got our data reduced with about 3 months delay. You know, we were 3 months behind. Sometimes we were 6 months behind, but usually I was trying to keep it to 3 months. Now we have the data presented to you on the sphere the next morning. So you get your results immediately. And that means that you more quickly notice that when something exceptional happens. And that makes it possible to actually put out warnings and say, look, there's something going on. Hey, go out if you can, if it's clear. And you may be seeing something interesting.
Yeah, so the conversations will last for eternity, but then time is the bound. So I guess we'll stop here. So thanks, Peter, and thanks, Siddha. And I also want to thank Sahyadri for the great experience. Like, it was an amazing session. It was a wonderful session. And thanks a lot for taking the time for the session and taking us all through the life of a meteor and explaining about the CAMS network. Yeah, so on the behalf of Celestic Club, I would like to thank all the participants for joining the session and for all the interactions, which were really wonderful. I also want to thank the faculty coordinator of the club, Dr. Jesse, for the permission to have this event, and the IT department for allowing us to use the Institute's Zoom conference account. Finally, I want to thank all my friends who worked on making the event a success, who worked really hard for making the event a success, and I want to thank them also. Finally, once again, thank you, Dr. Jenskins and Ms. Siddha, for the session, and have a great night. So we'll be back with more wonderful sessions. So until then, stay tuned, stay safe.
That's good. And if you do find a meteorite, take a picture of it with your cell phone in daylight and send it, and we'll have a look. Be happy to give my comment on whether I think it's real or not.
Thank you, guys. Thanks a lot.
Thank you.
Bye.
Bye.
Bye. Nice day.
Yeah, have a great night.